Overview for the solids of revolution. You have three main categories for the solids of revolution. You can use a disk method, a washer method, or a shell method. Which method you use really is dependent on the shape or the region that you're trying to revolve. I'd like to go through as an introduction and explain each of these methods. As we've already learned with the disk method, if this is my set of XY axes and I have a simple shape, say something like y equals rad x, that's being revolved about the x-axis. As it gets revolved about the x-axis, it creates this three-dimensional shape, almost like a bullet, and say we're going from 0 to 4, we'll put x equal 4 there. As that creates that three-dimensional shape, there is no void inside here. This is a solid shape, and we can simply see that we would have disk after disk after disk after disk that could be stacked in there. And so we would rely on that formula that your volume would equal the integral, in this case from a to b, would be 0 to 4 pi, and the radius is defined as the distance from your axis of revolution up to your curve, which would be rad x squared. So it's pi r squared. R was rad x, so I'm going to call that radical x squared. And the dx is the distance between, or the height for each one of these disks. That's the height of that. And so we call that dx. So it's pi r squared h, 3 dimensions. And we would call that our disk method. I'm not going to do the math, I'm just trying to introduce the concept. So then we learned about the washer method. The washer method, say we had the same shape here, that radical x that was shooting up like this, y equals radical x. This time, however, let's put the line y equals x. And we can revolve this too about the x-axis. So we'll continue to revolve this about our x-axis, and that would create, once again, a three-dimensional object. So as we revolve this, we're going to get this shape. If you look at that as a three-dimensional object, by the way, on this one we would be going from 0 to 1. So we got x equal 0 to x equal 1. And you look at that shape, you can tell that this cone is being removed from that bullet shape. And so as we set up our volume, we can say that the volume is equal to the integral from a to b, which in this case would be 0 to 1, pi, and then what you're looking at is you're squaring each piece. So it's going to be pi r squared dx minus pi r squared dx, but oftentimes we just write it like this. We say, what is our big radius? The furthest distance out that you go from your axis of revolution. It'd be your rad x. And since that'd be rad x, we're going to say rad x that gets squared, that's pi r squared, minus our shortest radius is just x, so we would say x that gets squared, and then we would do our dx. We use that formula of pi big R squared minus little r squared dx to show that there's a void, that we're removing a piece of this. And that's what we're looking at when we do our washer method. So this would be your washer method here. That's your basic formula. And then we go to the new concept. The new concept is this thing called the shell method. The shell method, instead of stacking discs or washers, you're really going to be considering this. Let me write up here, shell method. Like the shell of cylindrical shells. The way they explain this, think of a paper towel roll. You got a paper towel roll, looks something like this. If I were to remove a shell of this, it would be a giant rectangle. So if I unravel my paper towel roll, this rectangular piece would wrap around that shell. And I could do this repeatedly, again and again and again and again. Pardon my crude drawing. But as I start to put this all together, hopefully this will start to make sense. So if I take one pass around this paper towel roll, I realize that the distance around here is 2 pi r. It's a circumference. And then I have the height, which I'm just going to call h. So for one shell, I could find this area just by taking 2 pi r h. That gives me that area. But if you recall, the solids of revolution are really talking about 3 dimensions. So we would then have to consider how thick, how wide is this piece of paper towel? So when I rip that off, what is the depth of this? And the depth, well, that would be our dx or dy, whatever the case may be. And there's a little bit of a catch on this, because when we do our axis of revolution, it's actually going to be a little bit reversed. And I'll show that, I'll explain that here in an example. Let's start with a brand new problem, and I'll try to explain how you would set this up. Let's say that we had, I don't know, something odd here. Let me grab my calculator. So my calculator, let me have y equals, let's go with our square root x. So we'll graph that. And then maybe we have, for a second curve, something like y equals, actually let's just stay with that. Let's just stay with rad x for a second to explain what's going on here. So we'll draw our curve, y equals rad x. Now, this would be easy to solve for x. It's already solved for y. You could go back and forth on this. But let's pretend like this was something really nasty that we couldn't change for. We couldn't solve for x. So get everything in terms of y. And on this problem, what I want to do is I want to revolve about the y-axis. If I revolve about the y-axis, you would want everything in terms of y. In other words, you want to solve for x. So it would be x equal and then a bunch of stuff in terms of y. I'm pretending on this problem that I can't solve for that x. I can't get the x by itself. And so the shell method is really what we want to use, because what it will do, it allows us to say our volume will equal. Now I'm going to set this all up. Stay with me, bear with me here. We're going to go from 0, so we got our x equals 0, and let's say we'll go out to x equal 3. To x equal 3. So I've got x equals 0 to x equal 3. Now if you're comfortable with the disk and the washer method, you should be scratching your head saying, wait a second, if you're going about the y-axis, shouldn't everything be in terms of y? No, that's the beauty of the shell method. If your function is nasty and it's something that you can't solve for so that you get everything in terms of the y, we've got this fix called the shell method. It says, well, we can do everything about the y-axis, but we can do it in terms of x. And how we do that is simply like this. Our formula we're looking to go 2 pi, whatever our radius is, so I'm going to call that little r for radius, whatever our height is, and then we'll have a d something. It's either dx or dy. In this case, it'll be dx because I'm going about the y-axis, so it's reversed. It's the opposite of what we've been taught with the disk and the washer method. So this is going to go dx. And now let's explain how this works. So I'll start with a 2 pi, which is simple. The radius, well, the radius means you have to be egocentric. You have to be centered at your axis of revolution and say, well, where am I going? You're going to go so many units to the right here. As you go so many units to the right, I'm going to call that x. I'm going x units this far. Don't know how far, just x units. So my radius becomes an x. And this will be a point that I have to explain better in more examples. The height. So at any distance that I went out here, any x that I went out, the height, in this case, just happens to be my curve. It's rad x. And then if you're imagining this being revolved, again, we're using our paper towel model as an example here. We're thinking about this thing where we've cut out that central part. If you think of this as a three-dimensional object, I can go from my axis of revolution out. That distance is called x. However far you want to go here, you go here, you go here, you go wherever. That's x. I have a height that is defined by that curve. And as you do one lap around, one paper towel, so to speak, that would be an area, but it has a depth that is infinitesimally small, which we're calling our third dimension dx. So I've got 1, 2, 3 dimensions. Radius, height, and then I put my dx right there. Which means that when I want to integrate this, I can go from 0 to 3, 2 pi. Now, x times rad x is just x to the 3 halves. X to the 3 halves dx. Now, integrating that would be fairly simple to do. Or I could put it in my calculator and come up with the answer, which would be the volume of this region that's been revolved about the y-axis. So there's our introduction to the shell method.